Sometimes power series are the best or the only way to solve a differential equation. A power series has the form of the sum as n goes from 0 to infinity of c sub n x minus a to the n, and the terms look like c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a quantity squared, and so on. In our work, a is going to equal 0. So the sum as n goes from 0 to infinity of c sub n x to the n becomes our series. And that looks like c sub 0 plus c1x plus c2x squared and c3x cubed, and so on. It's really important that you grasp that this is the form of a power series. And when we find solutions to differential equations that are represented, the solutions represented as power series, what we're really looking for are the C0, the C1, the C2, the C3. Those constants are what define a particular function as a power series. Now for a quick definition, a function is analytic at a point A if it can be represented with a power series centered at A with a radius that's not 0. That means over some interval. And remember that in our work, A is going to be 0 when we're solving differential equations. The textbook we're working with does get into radius and interval of convergence for power series and some of the tests that you saw in second semester calculus. I'm going to bypass that because most of the work that we're going to do is with these types of sigma expressions here. We have this sum as n goes from 1 to infinity of n cn x to the n minus 1, plus 3 times the sum as n goes from 0 to infinity of c sub n x to the n plus 2. We're asked to rewrite the given expression using a single power series whose general term includes x to the k. I'll tell you, we're going to have more than just that single power series, but you'll see as it unfolds. Our basic plan here is to first make exponents match and then make indices match. And indices are the starting point for the sigma expressions n equals 1 and n equals 0. We'll do it in this order every single time. If we don't, problems arise. For the first sigma expression, we have x to the n minus 1, but we want to express that as x to the k. Therefore, we're going to make a substitution that n minus 1 is going to be represented using k. I'm going to go through a fairly formal presentation here that I won't really reproduce as the chapter unfolds. If n minus 1 is equal to k, then n is equal to k plus 1. Okay, everywhere we see n minus 1, we're going to replace it with k, and everywhere we see n, we're going to replace it with k plus 1. We have the sum of k plus 1 times c sub k plus 1 x to the k. We've achieved what we wanted with the exponent, but we've made a change that affects n, and it needs to affect n everywhere we see it. If n is equal to 1, then since k is n minus 1, k equals 0. The infinity is unchanged. It's still going to be an infinite series. And all of that was the formal approach, which I generally don't use. What I generally will look at is if I have an x to the n minus 1 and I want that to look like k, then we have an apparent change of being bigger by 1, right? Because here we have an n minus 1 and here we have just regular k. There's no minus 1. So it looks like it got bigger. What really happened is we changed the meaning of the variable, but that's a little more than I want to get into. And then when we had c sub n, we again made that look bigger by writing it as c sub k plus 1 through the substitution. And likewise with n, it got bigger with k plus 1. All those instances of n got bigger. And so the starting value for the index needs to get smaller to compensate for the fact that all those got bigger. If you were to plug in n equals 1 into ncn x to the n minus 1, what you get is c sub 1. If we plug k equals 0 into k plus 1 c sub k plus 1 x to the k, we get c sub 1. It generates the same terms, but we've relabeled what the variable means essentially. So using that lens, we're going to treat the second sigma expression. Now, I've noticed in my work that we have here the 3 in front of the sigma. If I leave that 3 out there, I'm pretty likely to forget that it's there. So I'm going to bring it inside the sigma. And then we want, instead of x to the n plus 2, we want that to be x to the k. So x to the k. And it looks like what's happened is we've made that smaller by 2. I mean, we haven't. It's just a substitution. But then when I see c sub n, I need to make that smaller by 2. So I'm going to call that c sub k minus 2. And then we compensate for it. N was 0. These k's went down by 2. So I need to make that k go up by 2. So we have here k goes from 2 to infinity. We've now made the exponents match. Now I want to make the indices match. If I were just to change this k equals 0 to k equals 2, then I would have to change all of the k's here, and then we would lose the work that we got with the exponents. That's why we start with the exponents, we go to the indices so that we lock in those exponents. But if we look back up here at the power series as n goes from 0 to infinity of c sub n x to the n, the first term was c sub 0, the second term was c sub 1 x. If we wanted to, we can stop the plus expressions at any random point and express it as a sum of c sub n x to the n. And here what I've done is I've stopped it where n is equal to 2. So we've got c sub 0 plus c sub 1x plus the sum as n goes from 2 to infinity of c sub n x to the n. We've achieved raising the index by writing down the terms that we get from the index values smaller than the one we started with. Yeah, okay, that was a little convoluted. We need to do essentially the same thing we just saw. I want, instead of k equals 0, I want it to be k equals 2. Once the exponents match, we have like terms. Once the indices match, we have like sigma expressions. The bottom line of all of that is that we need to write down the terms for k equals 0 and k equals 1, so the blue sigma can start at k equals 2. If k is equal to 0, then we have 1 times c sub 1 x to the 0. We already saw that. If k is equal to 1, then we have 2c sub 2 x. And then what's left is a sigma expression that starts at k equals 2, goes to infinity. We have our k plus 1, c sub k plus 1 x to the k, plus the second sigma expression, which also started at k equals 2, goes to infinity, 3c sub k minus 2 x to the k. We want to combine these into a single sigma expression. There's no way around writing down the c sub 1 and the 2c sub 2x. Combining into a single sigma expression, since they both start at 2, our sigma expression starts at 2. Since they both have factors of k, x to the k, we have our x to the k. And then we have our k plus 1 c sub k plus 1 from the first sigma, plus 3 c sub k minus 2 from the second sigma. That becomes the coefficient of each term